All right. I believe we are live. Welcome back, everyone, to the Chainlink Fall Hackathon. We have some great guests here this morning. Our topic is Bringing Muhammad to the Mountain, Compute over Data hosted on IPFS and Filecoin. And with that, I'll drop out of the stream and leave it to Kai and Arena.
Thank you,
So,
Jamie.
hi everyone. So, welcome to the webinar for Bringing Mohammed to the Mountain and Compute over Data hosted on IPFS. And we'll be today presenting Kai and me. Kai is our lead engineer on the project, and I'm developer relations. And we both work on Protocol Labs for the project, which is named Bacalhau. This is a very fun word that I haven't knew before I joined the company, before I joined the project. And to give a little context about the Protocol Labs, so our experience is all around decentralized peer-to-peer storage technologies such as IPFS and Filecoin. And significant portion of our team are network engineers or cryptographers or researchers like Kai. So a lot of work in the past was done around bringing large data sets and putting them on Filecoin or IPFS at little or no cost. So I will start this presentation to walk around what is Bacalhau and why we need it. And then Kai will go through a bit more like under the hood how Bacalhau network works and show us amazing demo. So let's get started. So what is Bacalhau? Bacalhau is think of it as a distributed computation over data, system of distributed computation over data, where anyone can join the network, anyone in the world, and offer their compute resources. And also anyone in the world can join the network and request for the resource for their jobs to be run on the network. And Bacalhau is really efficient on running jobs over IPFS data. So just to remind, IPFS data is decentralized and public. And the network will find the most efficient way of running the data. And it will be using like market forces. So you don't need to run it, download the data yourself, or large data on your servers or on the disks and pay for the network or for the disk resources. And this is also a self-sustaining marketplace. And for doing this computing, and in the future, we will also offer a token for it. So why we need Bacalhau? Bacalhau is good with data, with large data that has a gravity, right? So we talk about large data that is like petabytes of data that is very expensive to download or copy over the like ingress and disk resources. And it also very slow of copying this type of data. And the large part of the kind of the whole strategy of Bacalhau, how to optimize computations over this large data, because it's so expensive. And also let's remind ourselves that usually our source code, like algorithms where we want to run these computations over this data, is usually small, right? So scripts are incomparably small, like kilobytes of data. If we run executable on it with all the libraries, it's megabytes of data, and they're like very small. So Bacalhau is distributing computation over these like large data sets. So instead of sending data where the job lives, it would make more sense to send job where the data lives, and that's where compute over data name is coming from, and that's where it's acronym for code, and code in Portuguese is Bacalhau, and that's we get the name of the project. So let's kind of walk over through what problem does it solve again. So Bacalhau is is a network that will process very efficiently large data sets that lives on IPFS network, and also aim to compute any language, any workload, and abstract away all complexities around like smart contracts, around so developers don't need to learn any new languages. Everything stays like the same, and also abstract away all the complexity with that data management. So what jobs can you run on the Docker? So it's a Docker container. So you just need to put your executable into Docker container and send to the network, or it's WASM. So this is WebAssembly for portable binary format. It was made for the websites, but because it doesn't link or doesn't provide any additional features for the web-specific features, it can be used in other environments. So we use it and for in Bacalhau, and usually all languages provide some sort of support for it. And if you for your data to process your computations as an input, you can input data from IPFS, or you also can set up a URL where the data will be downloaded from automatically by the network, and outputs of your computation, the results of your computations, will be stored in IPFS or Filecoin. You specify it yourself. And let's also, you might also wonder, like, okay, what's the difference between Bacalhau and other kind of frameworks, large number of frameworks that offer processing of generic large data sets? For example, what's the difference between Bacalhau and serverless like AWS Lambda? So I would say that the most so it's good if you want to run a website and you want to run you want to put your backend of your website on the AWS Lambda. This is a good example. Or if your data leaves an S3, because then you don't need to move anything, but remember that it's centralized Web2 technology. Another question that we receive is like, what the difference between Bacalhau and World Computer? This kind of what Ethereum founders wanted to build in the beginning, and Ethereum is quite kind of very expensive and extremely correct world computer. Just to remind you that when you send your smart contract and list of transactions to the blockchain inside your block to run, that every node in the network has to produce these computations, and sometimes this is not what you want, and it's quite expensive as well, especially if you want to run it over big data, which means every node on the network has to download this data and store it somewhere. And other example is Spark, which is just to remind you, it's in memory only, and it provides a specific exotic language that developers has to run the code on, and then Spark will automatically kind of identify how to run it on the cluster, and there should be entire cluster dedicated to run these computations. And yeah, user experience is very very low, I would say, there, because whatever it takes in Python, like 5 lines to write your algorithm, in Spark it will take 50 or 100 lines. So Yeah, just to remind you, Bacalhau is language agnostic. You just put your executable code into the Docker container and send to the network, and network will find the most efficient way to run it and the most cheapest way to run it. So, and from here, I would invite our lead engineer Kai, who works on this project and who's been building it from day one, to kind of give us a bit of understanding of how Bacalhau works under the hood and what protocols it uses, and to show us a little demo.
Awesome. Thank you, Irina. That was an excellent summary of the project. I'm going to attempt to click some buttons and share my screen. So hopefully this works fairly trivially. This is always that stage in any technical situation where we're reduced to finding simple things. Okay, so yes, okay, I think we have.
Yes.
Can you see my screen, Irina? Excellent.
Yes.
Okay, here we go. So, oh no, I clicked the wrong button there. This is what I mean right now. Okay, slideshow. That's us. Awesome. Okay, so what I'm going to do is just give you a rough overview of like the high level flow of a job through the Bacalhau network. Then we can have a look at the kind of internal architecture, understand how these various bits fit together, and then try a live demo. Let's see what happens with that. So Bacalhau, as Irina has said, is a distributed computation network. And the point of it is to run compute next to where the data lives, because data has gravity. And the compute job is tiny and the data is big. So let's reverse the paradigm and send the job out to where the data lives. What is the network? Well, we've built Bacalhau on the same stuff that IPFS and Filecoin is built, which is this awesome library called libp2p. It gives you various constructs to build a decentralized network. One of them is gossip sub. Now, it's worth noting the approach that we're taking at the moment will change, right? So this is Bacalhau today. We're going to introduce some libp2p protocols and node-to-node direct communication. But the essence of what I'm going to show you now will remain. It's just a slight rearrangement of network topology, but let's go through it. So we have a network of nodes, all peer-to-peer. There's no central server. They're all connected to each other over libp2p using gossip sub. And gossip sub is a pub sub network, it just without a central coordinator. So it's like, hey, I need everybody to hear this message. So you're going to send the message to the nodes immediately connected to you. They will then turn around and forward it to the nodes immediately connected to them. And before you know it, the whole network has heard your message. So let's visualize that. The message propagates out to every node in the network. So if we wanted to tell the network, hey, everyone, I have this job that I want to run, we would use gossip sub to tell everybody that the job exists. The idea then is like, how do we actually do that? How do we, as a client, initiate that process? So we have a CLI, and that speaks to a REST API. It says JSON RPC here. It's actually a REST API. So you can see this slide is slightly old, but oh well. You can communicate with Bacalhau as any other application over a remote HTTP endpoint. So you can write clients, you can write code that initiates Bacalhau jobs. One use case that we have in our mind actually is this could be really useful for CI jobs. So it's like, hey, I have this long running thing. It has to chunk through loads of data and produce an artifact at the end. The CI system, GitLab, GitHub Actions, any CI system that you're using, as one of its steps, it could initialize a Bacalhau job and wait for the results to come back. So the computation is happening outside of wherever the CI runner is. There's a good use case of how we might use a client CLI / code that speaks to the HTTP endpoint to initialize the job. So we send the job in. This little orange box is the job. And using this gossip sub thing, the network hears about it. This little screenshot at the top is just an example of like, hey, this is us using the CLI. What is a Bacalhau node? What are these things? If I go back one step, what are these gray boxes on the network? Well, they consist of 3 parts. The first part is the API server, which is a REST API now, but it's, that's this box. It's the thing that accepts requests on behalf of the client. You then have this entity called a requester node. That's the thing that looks after a job, because it's basically you're saying to the network, hey, can you please run this job? You connect to one node that you trust, much like Infura is a wallet gateway. You trust Infura, you can always move somewhere else. It's decentralized. The requester node is a similar concept with Bacalhau. You send your job to a requester node. It will then look after the life cycle of that whole job. Because let's face it, you may be sat in a coffee shop. You run a job that might take 6 hours. So you're going to initialize that job sat in the coffee shop, go home. In the meantime, the requester node is looking after that job for you throughout its whole life cycle. The compute node is the other side of this. These are the things on the network that have CPU, memory, disk, and GPU to offer up to the network to run jobs. So the basic flow is the client on the left here communicates to a requester node, says, could you please run me a job? The requester node publishes that out to the network on Gossip Sub, and all of the compute nodes pick that up and they bid on the job. They say, I'm willing to run this job, or they could ignore the job and say, I don't want to run it. The fact that there's a requester node on one side that is essentially like the long-lived client of the job. The custodian is a word I've enjoyed using. It's of responsible for the life cycle of the job. And then multiple compute nodes all coordinating with each other to finish the job. So these are the three main components in the network. This line just represents its one node, these three things. So let's talk about data gravity. Irina touched on this a little bit, and it's kind of the whole point of compute over data. It's this idea of like, this job will require these inputs. Do I have these inputs locally? Therefore, if I was to take this job on, it wouldn't cost me loads of money in ingress fees and loads of money in disk space. So we're calling this self-selection. It's this idea that a compute node out on the network sees a job arrive and it says, hey, do I have this data locally? So let's look at what that would look like in the case of the answers being no. So the job comes in, it says the input data for this job is this CID right here. The IPFS node that the Bacalhau compute node is sat next to, because that's the topology, is you have an IPFS server with its disk with all of the blocks on that disk, and next to, as in when I say next to, it could be running on the same machine, it could be running on a machine on the same LAN. Ideally, it would be running very close to where the data is to prevent network costs and etc. So in this example, we've got a job with this CID. The compute node next to the IPFS node will check all of the CIDs that are actually local and say, well, I don't have that one locally, so I'm going to pass on this job, because it would mean I'd have to go out onto the public DHT of IPFS and download all of that data in order to do the job. In reverse, so you know that red up here represents like, I'm going to pass on this one, thank you very much, right? The next one is a CID comes in, and this time the IPFS server does have the data locally. So it says, okay, I'm going to bid on this job because it's going to be much cheaper for me to run this than somebody else who has to download it. So in a kind of visual sense, that's what we're talking about when we mean because data has gravity, we need to be aware of CID locality and self-select jobs based on that. A bit of a mouthful, but I think we kind of can string that together based on what we've said so far. So to see a kind of overview of what that flow looks like, the CLI submits a job through the API server, which hands that off to the requester node, at which point the laptop that submitted the job could close because the requester node is the one now responsible for the job. That propagates it out to the rest of the network. The rest of the network will do this CID self-selection, i.e. bid on the job if it's worth doing because the data is local. And that is the general overview of like compute nodes being aware of data locality, basically. So if we go into like peek inside the box a little bit, because I think this is where we've, I've skipped over a large number of the more important concepts, like how do we verify that people are telling the truth is quite a big one, and where do the results go? And Irina mentioned a few times, which is absolutely spot on, like, what types of jobs can I run? And Docker and WASM. So how does that actually work? So this is the overview of what's inside a Bacalhau node. I'll just kind of fairly roughly talk about each section, and then we can go through the other slides, which goes into a bit more depth about how all of these things fit together throughout that life cycle that we just saw. So CLI speaking to the requester node, we kind of don't have the HTTP API, which we noticed on the previous slides. That just lives here. So it's like the CLI speaks via the REST API to get to the requester node. The requester node, as we've said, is the thing that's the custodian of the job. It's going to broadcast the job to the network. It's going to sit back listening for bids that come back in. It's going to decide which bids to accept. It's then going to perform the verification on the results that it hears about. We'll talk about that more. And then it's going to trigger I accept these results and reject those results, which ultimately ends up in the compute nodes publishing those results. I think it's a long running process on the network that is looking after any jobs that have been communicated to it by the CLI here. The transport is an interface. So the point of me saying interface is, like in this diagram, you can see it says, for example, libp2p. It would be very possible to switch that out and use a different transport. So, for example, in our tests, we have an in-memory transport because then it's much faster and we can get through things much faster by doing it in process. So the job of the transport is to communicate with other nodes anything pertaining to a job that they're looking after or a new job that comes along in the network. So it's kind of does what it says on the tin. Its job is to transport messages between nodes in essence. The compute node is this side. It is possible to run like a single Bacalhau process that is both the compute node and the requester node, but logically they're separate entities. And realistically, if you're deploying a Bacalhau node, you'll be thinking, I'm joining the network as a compute node. So you wouldn't run the requester node at the same time. Equally, service providers would say, well, I'm going to run the requester node so I can allow people to submit jobs to the network. And they might not be interested in running a compute node either. It's completely up to the person installing and running the binary, which of the two or both that they choose to use. The compute node itself on the left-hand side here has these sort of core components. The executor, the thing that runs the job. The storage provider, the thing that provides the inputs to that job. The publisher is the thing that sends the outputs of that job off to somewhere else. The verifier here is the thing that coordinates with the requester node. As you can see, the verifier is on both sides to decide if a compute node was honest or not. You can see here IPFS is an example plugged in as a storage provider. Estuary is an example plugged in to the publisher. So it's very important to note that all four of these things here are also interfaces. And what I mean to say is it's pluggable. So it should be fairly trivial to rock up. And for example, let's say Cloudflare Workers is another place to run jobs, or WASM is an example that's not in this diagram, but we have a WASM executor and a Docker executor. We have an IPFS storage provider and a URL-based storage provider, and soon to come, when it's functional, a Lotus Filecoin retrieval markets storage provider. So the concept of Bacalhau is to enable lots of different modules to be plugged in to perform each of these roles. It's not where it is a Docker system with IPFS and it publishes to Filecoin. It's a thing that runs your chosen executor against your chosen storage inputs that publishes to your chosen publisher. So I think the key thing there is it's more of a framework that enables you to run the job using the various characteristics that your job wants, right? So it should be fairly trivial. It is fairly trivial to write new modules for each of these interfaces because they're not complicated interfaces. So having said that whole spiel, that's basically kind of an overview of the whole map of all of the bits and how they fit together. So let's sort of trace, if you like, the flow, a day in the life of a job on Bacalhau. So the CLI submits the job to the requester node. The requester node uses the gossip sub network over libp2p to broadcast the existence of that job to the whole network. All compute nodes hear about that job. You've then got that self-selection step that we saw just earlier. Like, hey, is it a job that I'd be interested in running or not? The basic level of do I want to run this job is, do I have the data this job requires local to me, right? And that can be done automatically. As in, you can configure the compute node to speak to an IPFS server, and the compute node will say, hey, IPFS, do you have that CID on your disk? If it says yes, it will accept the job, right? Then there's more complicated setups for deciding if you want to bid on a job. For example, it's like, is this a Docker job? Is it Tuesday? In which case I don't work on a Tuesday. There's all sorts of different things that might affect the compute node's decision as to whether it's interested on bidding. And for that, we have HTTP and exec hooks. So if you're a compute node provider that wants to only ever work on a Tuesday, for example, you could write your custom hook that says, only if it's Tuesday will I say yes. And that's totally up to you now what code you write that in. It's up to you if you run that as an exec hook or it's a HTTP server somewhere. We're trying to kind of allow people to bring their own logic for making these sorts of decisions, as opposed to define it all ourselves in some complicated DSL. So move past that step. Let's say, yes, the compute node does want to bid on this job. So that would then go back as a bid to across the libp2p network back to the requester node. And this is this orange box here. Having decided yes, either by like automatically asking the IPFS, do I have the storage locally, or asking an external hook. If the answer is yes, it will then bid. So if we move to the next thing, the kind of opposite situation is now happening, where the requester node is hearing about lots of different bids. So which bids should it accept? Well, this is an interesting question. For the same reason, there may be various different logic that the requester node, the person that's submitting the job, wants to use to decide which bids to accept. On our roadmap, we have the concept of reputation system, and that will be linked to the token that we issued to pay for these jobs. This is stuff that we'll talk about further down the roadmap. That stuff, however, comes really into play when we're talking about which bids should I accept, because clearly if there's a compute node that has a really bad reputation and there's a compute node that has a really good reputation, you're going to pick the one that has a good reputation to run your job. So this step of, I just heard about a bid from the network, it's very possible to hear about a bid and wait as well. We have various configurations of a lower level threshold on how many bids should I hear before I even think about which ones to accept. And that creates an interesting scenario where, the requester node is basically sat back going, it's kind of in a weird way like an auction. It's like, which bid comes in that I'd prefer is the one that I'm going to pick. Moving past that, it's going to issue a I accept your bid message back to the network for the compute nodes that it accepted, and it's going to issue a rejected bid to the ones it's rejected. And that's, like I said, that's completely up to the requester node, and what custom logic you plug in is up to you to which bids to decide. If you leave it alone, then it's a first come first serve basis once those minimum thresholds have been met. But as I say, later on we can talk about reputation systems and such things. So the moment a bid has been accepted, essentially that's the point at which we've made a deal, right? It's like, hey, compute node, you said you'd do this. I accept your offer to do this. That's, again, sort of talking roadmap stuff for a second. That's the moment at which we would make a deal on chain. Up until that moment, we're kind of negotiating with machines off chain, right? Because it's when you say, I agree to this, is akin to signing the contract. I am now liable to do this. That's the deal that we will push to the smart contract living on chain. Whether, most likely that's going to be running on FVM as an Ethereum contract, but we are still working out the options there. That's a roadmap issue. It's very much the intention of the project to have a smart contract at the core of this bidding acceptance payout once the job has finished process, though. So it's worth kind of planting that flag at this moment. Like, whilst at the moment this is a libp2p network with no consensus mechanism, we absolutely will have consensus in the core of this network via a smart contract running on FVM or Ethereum, or maybe both, who knows. Right, so once the bid's been accepted, the deal's been made, whether that's on chain, at the moment it's just a libp2p message, the compute node now kicks into action and actually runs the job. So this is the responsibility of the executor based on how the job is configured. So if the job was submitted as a WASM job, it would trigger the WASM executor. If it's a Docker job, trigger the Docker executor. The storage providers, which are essentially the inputs to this job, will kick in. And it's important technical, it's almost a boring technical detail, but it is important if you're looking at this project the first time. and you're trying to make sense of like, how does an IPFS volume work with a Docker container and also with a WASM runtime? And clearly these are very different beasts. So if we are running a Docker container and we want to consume an IPFS volume, it's going to be with a POSIX volume mounted as a Docker volume, and it's going to manifest itself as a file system. This is the Docker executor's opinion of how it consumes an IPFS CID. If we have a WASM runtime, the IPFS CID may be the same thing. I might be sending the same CSV file or image set into both Docker and WASM. How WASM will work will be very different. It will offer a library stream, a streaming library call, basically, to say, list the files in this CID, stream me the bytes in that CID. It's a very, very different way to present the storage, even though the upstream storage is the same thing. Which executor you're using will decide very much on how it manifests itself into your job. And that's kind of an important statement, because it means that essentially, like, you know, the WASM workload operates in a very different way on its storage as the Docker workload operates on its storage, even though it's the same upstream thing. Okay, having said all of that, what is the job? Well, it's completely up to you. Any Docker container that exists can run on Bacalhau. You can mount any IPFS CID into that container, and now your imagination is really the thing that decides what the job's actually doing. Once that's happened, we're going to produce some results, right? Now, what are the results? The results is a local folder, local to the compute node, of files on disk. And now a job can decide not to produce any files on disk. Some jobs might be useful just to print a standard out stream, right? Hey, do this job and just print the number to me on standard out. We'd still call standard out a result on disk. And how Bacalhau works is it captures those standard out streams and standard error and exit code and writes anything that's useful that the job's produced to a folder on disk, as well as any additional folders that you've explicitly written to as part of the job. So a good example is just take two quick examples of different types of job, right? One job is, hey, download this CSV from IPFS, add up all the numbers and print the result to standard out. Another one might be, download this folder of images, run image magic, and resize all of the images and put all of the resized images in an output folder. So both of those would just end up with a folder of the results on the compute node once the job has finished. If we go to the next thing, this is then where it becomes quite interesting, because the question might be like, how do we know that that compute node has done the correct work? What's to stop somebody rocking up and just going, I'm just going to pipe dev null and then, you know, submit that as a result? And how the hell is this system going to know that that's the case? So we spoke about reputation systems. That's one way that we can do that. Hey, look, if you try and do that, then your reputation might hurt, etc., etc. But realistically, we need to try and verify the results somehow. So it's very important to talk about deterministic jobs, right? So there's two things to talk about determinism. There's like sources of entropy in the runtime. So for example, hey, I've got a Docker job and it's going to read from the clock, and that is then going to print in a log file that's produced. Damn, that's non-deterministic. If I run a Docker job that doesn't read from the clock and always does the same thing, even though the environment that the job is running in has sources of entropy, the job itself is deterministic because it produced the same results. In WASM, it's much easier to guarantee determinism because you can remove the sources of entropy from the runtime. Statement of fact, at the moment, Bacalhau works with deterministic jobs when it comes to verifying them. So things like training AI models and inherently non-deterministic things won't work very well with our verification system as it stands today. So it's important to note, like resizing, using image magic on a set of images, it has a deterministic result, right? The images will be the same produced between two computers, even though they're running in a runtime that has entropy. So the reason that the jobs themselves have to produce deterministic results is because of the way our verifier works. So the first statement would be, you would run the job on 3 different nodes or a number of the client's choice. And that's really down to how trusting the client wants to be of the network. And it's the client's option to run it on 3 or 7 or totally up to the client. The next step is for the executors to run the job, and each of them will bid separately. So, and the requester node will accept the number of bids that the concurrency setting is. So if we work with the number 3, right, I'm like, hey, network, run this job, but I want a concurrency setting of 3, right? So it's the same job being bid on and accepted the bids 3 times, because we need 3 copies, and you can't run 2 of these copies on the same machine, right? They have to be completely different compute nodes, otherwise it kind of defeats the purpose. Once a compute node has produced a folder of results, it will hash that result. And so now we have a hash of the results it's produced. And we send that hash back to the requester node, to the verifier running on the requester node side of things. But before we do that, we encrypt it with the requester node's public key. Because obviously, if we don't encrypt the hash, and I'm a cheating compute node, I'll just sit back and I'll just wait for the other compute node to do the work, wait for the message to go back to the requester node that has the hash in it, and I'll just go, yeah, me too, I also came to that hash. So in this system, you can't just copy somebody else's results, because it's only the requester node that can decode your verification proposal. What's a verification proposal in this mode? It's an encrypted hash of the results that were produced. So the requester node sat back, it's hearing all of these verification proposals. Once it gets quorum, okay, I have 3 in, and the concurrency setting was 3, it's going to make a decision. Now, clearly, if one of those 3 nodes didn't do the correct thing, the hash will be different. And so the requester node can make a decision on that basis. It's then going to accept or reject each of these proposals. Very important to note that the deterministic hash verifier is just one implementation, and the verifier itself is an interface. So as soon as we start to come up with interesting other ways to verify work in this decentralized manner, we can plug in other verification modules, and the person submitting the job to the network can choose which, how many nodes should run this concurrently. What's the minimum number of bids that I need to wait for before I'm going to make a decision? What's the verification module that I want to use for this job? So for example, if I had a non-deterministic job like training an AI model, I might decide to still throw it out to the network, use no verification module, and rely on the reputation system in order to which bids am I going to choose. The real key point I'm trying to make is that it's our job to make a library of options rather than have a strong opinion about how it always should be, right? Because we just didn't know. Each workload is going to be entirely different. But for the sake of this example, let's focus on the deterministic job and deterministic hash verifier that we've just gone through. So requester node accepts or rejects these proposals, at which point the compute nodes kick in and then publish the results to a public source. We've used Estuary in this example because that will push it out to IPFS and Filecoin. There's a variety of other publishing mechanisms. We're going to integrate with Evergreen, for example, which is another Filecoin deal-making system to get the deals pushed out to Filecoin. Our default publisher is just push it to IPFS servers that we run. Again, the publisher is a module, so we can implement different versions of where the results are pushed once everything is finished. And so once the results have been published, the client now can get at the results of the job and see those results. So one step back is when we have the deal system on chain, this accepted or rejected message coming from the requester node will be the thing that triggers the payout for whatever deal was made. Smart people will be sat back thinking, what if the requester node lies? What if the requester node is the nefarious entity? And that's why we're putting the deal making system into a smart contract, because then we can hold escrow, and the requester node the requester node will stake the money that it's willing to pay for the job. And then if the requester node lies, the compute nodes will be able to collude together and demonstrate they did actually do the job. And such things can progress. So there's a whole world of different combinations of how these things can work. That is where we're currently at in the project, is identifying these various different flows, understanding how we need to make this smart contract work so that holes aren't found in that protocol. I think if we split apart the distributed computational network that we have today and the smart contract that will coordinate the deal making system in the core of it, we're starting to bring these two things together as our current phase and focus. So talks about publishing. When the results are out, it gets sent off to Filecoin or IPFS and you can read them. So I might just show you a demo of this stuff real quick, and let's see what happens. So let's grab this CID right here. Let's look at this CID on the Cloudflare network. So what this is just a few satellite images of our lovely Earth. I'm just checking I'm still connected. Okay, cool. Yeah. Checking I've not been chatting for 20 minutes and gone offline. So we have a CID that is a folder of images. Basically, if we look through all of these, you can see they're just on IPFS and they are satellite images. So if we take that CID, this is the one that we were just looking at, and we say, hey, Bacalhau Docker run concurrency 3, as in I need 3 nodes to run this so that I can be sure one of them didn't cheat. I could increase that to 10, except why 3 is just because I'm picking the number 3. It's completely up to the person submitting the job as to how confident they are in the network. Here is an interesting syntax like -v, which is normally the Docker syntax for mount an input volume. On the right-hand side, it works the same. I want this data mounted at this path inside the container. On the left-hand side, it's interesting because it's an IPFS CID. So that's neat. That's one of the kind of key characteristics of Bacalhau is like we're mounting CIDs into containers rather than mounting files into containers. And then we're going to run image magic across all of those files, and we're going to resize them to 100 by 100 and write the images out once we're finished. So let's see what happens when we run this. And this is when, if stuff's going to go wrong, it's going to be now. So, okay, we throw the job out to network. It's telling us that nodes have accepted the job. So we're just going to sit back here for a minute and wait for the results to come. And it says that the job has finished and it's verifying the results. Whilst that's happening, actually, what we can do is you can see we have a job ID right here. So what we can now do is we can go back, allow, describe that job ID. And we can actually start to understand the internals of what's going on. So we can see the job is finished just up there, but we'll just have a quick look down here to the describe output because it shows us a lot more detail of what's actually happening. So down here, this section is the job spec, right? You can see it's basically a data structure representing the CLI command that I put in. Anybody that's worked with things like Kubernetes will very quickly go, oh yeah, that's normal. If we scroll up here, this section here, though, is like, how did that job go as far as the network's concerned? So we have these various nodes on the network right now. We don't have a huge number of nodes. This is a demo version of things. So each of these is a node, right? And we can see this node ended up having its bid cancelled. So what that tells me is the job was already approved to other nodes. So this guy rocked up a bit late to the party. He said, hey, I'm willing to run that job. And the requester node said, oh, sorry, mate, like I've already given it to 3 people, right? This one here is a node that actually got the job. So you can see it's saying, hey, I've actually published this CID. The verification results was true, meaning it had the same result as all the other nodes. This is very interesting. So if we look down, we can see the other 2 nodes on the network that also did the job. They've all been verified. So you can start to get kind of sense, if you like, of what we were looking at in those diagrams just now, represented in the actual data structure from the network. So if we come up here now, and this, this output here is a summary of what we're looking at down here. The really important thing is, look, it's telling us, hey, get the results, Bacalhau get, fine, I could run that command and Bacalhau will get the thing for me. But to really trust this is what's actually going on, what I want to do instead is I want to look at the public IPFS network via a different source for this CID. So let's go to Cloudflare again, right? And let's say, hey, Cloudflare, what are you seeing as that CID? Because apparently Bacalhau just produced some data for that output CID. Oh, here we are. We have some stuff. Now, I think I mentioned earlier, like standard out, standard error, exit code also captures as outputs. But here we have a named outputs folder. This is where the resized images that we just ran were produced. And, quelle surprise, if we click on one of these images, we get a 200 by 200 version of the original image. So in terms of like end-to-end demo, there's a whole bunch of other things we can do. Like stable diffusion is the new hotness. That's the demo that was put together recently by the team to sort of demonstrate like, hey, if you have stable diffusion in a Docker container, you can send it prompts. There's a whole world of other features that we've got working now and are currently working on. I'll just rattle very quickly a few of those off, and then I'll hand back to Irina. So one of them is sharding, right? So hey, okay, I've got, I really like the image magic resize example, but I've got a folder of 10,000 images. Surely there's a way to run these faster than just one after the other. And the answer is yes, we can shard the job on Bacalhau. So sharding is like, given the 10,000 images, what would it look like if we split it up into groups of 100? And very much we can tell Bacalhau, hey, based on this glob pattern, here are all your atoms, group into groups of 100. And it will then distribute however many groups it's discovered in that CID as individual jobs and stitch the results back together at the end of it. So that's a very interesting thing. You can visualize that a bit like a DAG, where the job itself splits out into many, many parallel stages and then reconverges at the end. Speaking of DAGs, we're currently working on Airflow integration, where each step of an Airflow pipeline calls out to a Bacalhau job. We've got a lot of work going on with WASM at the moment, because we've got Docker this side, and what would it look like to have WASM workloads consume and manipulate CIDs? And there's a whole world of other things that we're busy working on. But hopefully that little demo gave you a sense of the overview of the project and why it's useful. So yeah, I might pass back to Irina now, if that's okay.
Yeah, thank you very much, Kai. It was tremendous. It was so good. Thank you so much. So I will share my screen again, and we'll direct. Can you see my screen? Yeah. And so, dear hackers, please go and scan QR code for documentation on the left. This is docs. This is the docs bacalhau.org, hackathon guide on the right. And please, engineering support 24/7 offered on Filecoin Slack. If you go to Bacalhau channel, and yeah, we are there. Kai is there.
Not 24 hours a day, but I am there vaguely.
Yeah. So thank you so much. It was great. And thank you, Kai, and happy coding to our dear hackers. And please join our Slack and check out our new Bacalhau platform. And I wish you all good luck. Bye.
Awesome. Thank you. Bye-bye.
Bye.